Okay, good afternoon everybody. I hope everyone's having a wonderful day. So today we're going to be talking about graph traversals. Now you might ask, Dan, what is a graph traversal? It's just simply, for us, it'll be the process of starting at a vertex u of the set of vertices of the graph. And all it is that we're processing all the edges and vertices of the graph that are so-called reachable from vertex u. So I gotta first explain this idea of reachable to you. So I thought I would draw a picture of a graph here for us, just so we can kind of really play around with this. So suppose that vertex u is A here. Now, what does it mean to be reachable? Suppose that I looked at vertex D. Now, the notion of reachable is very natural. So notice that there is a path that gets me from A to D, right? There's at least one. So for example, I could go A to B, then B to C, then C to D, right? So this would be an example of a vertex that is reachable from U, in this case A. So in contrast, if I were to introduce another vertex, say vertex I, is vertex I reachable from U over there? Can somebody tell me why it's not reachable? There is no path to I, right? So this is what I mean by reachable. So notice that there is no lines or pathways that get me to I. So this is what I mean by reachable. So what we're going to be interested in is processing all the edges and vertices that are reachable from U. So for example, if I had vertex I here, I would not be responsible for labeling or marking edges or vertices that get me to vertex I. However, all vertices and edges that could be a part of a path from U to any other vertex that's reachable, I'm responsible for processing those. So that's the idea of a graph traversal algorithm. It's actually quite similar to the idea of a tree traversal algorithm that you may have seen before, such as like pre-order, post-order traversals, or maybe possibly in-order traversals, say if you talk about a binary search tree. The same idea, except we're going to talk about vertices and edges. So are there any questions so far, kind of like the big game plan of what we're going to be doing here? So our goal is to process the entire graph. And the way we're going to achieve this is by marking vertices. So we're going to mark vertices. And we're going to label edges. So I would like to label all of the edges that could be along some path to a vertex that's reachable from my starting point, in this case, U. Now, the assumption I'm going to make, so this is an assumption, but we can make this assumption with all the data structures I've shown you, is that to mark a vertex, I could do this in constant time, and to label an edge, I could do this and also in constant time. You might ask, Dan, how is that possible? Is suppose that I give you a vertex. So suppose I'm exploring this graph and I follow along the edges. So I go from this, start at this vertex. I look at my neighbor. So I look at my incident edges, for example. From there I can get, for example, the access to both endpoints of an edge. If I have access to an incident edge, then I also have access to the edge itself. Imagine each one of these is an edge object, and in there I could store a label. So that's kind of the way I could think about how I could label edges. Another way is that now, because if I'm exploring across these edges, each one of them has an endpoint. Likewise, that means that each vertex has a vertex object, or you may have some attribute associated with a vertex. I can mark these as if I visited them or I didn't. So I have access to all of these things, so I can mark vertices, I can label edges in constant time under the setup that we have for our data structures, regardless of their representation. So anyways, that being said, I gotta talk about how we're going to achieve this. So I'm going to be showing you a couple of different ways to achieve a traversal of the graph. Today I'll be mostly focusing on so-called depth first search. Now, I'm not sure if you've heard of this phrase before, but we're going to focus on this idea of depth first search today. Depending on how far along, we might get to see the other one. So, you might ask, Dan, how are we going to explore this? This isn't like a tree where it's very natural for us in a tree to kind of work our way down the tree, and each part of the tree that I examine at a node or a vertex, each of that, recursively speaking, is another tree, right? And it makes it a little easier to play around with. I may know things about the children, for example, and I can recursively apply an exploration like that. So how do I do the same thing with a graph? So that's the first thing we're going to look at, and I'm going to do this through this so-called depth first search. So here's the analogy I like to draw upon to explain this. So think of the graph like a maze. So I'll call it a labyrinth. Where it's going to be a labyrinth where vertices. My apologies. Vertices are intersections. Are intersections and dead ends. So this is where, if you imagine you have a maze, like a really big maze. This would be, yes, exactly. Dance, magic, dance, fair. So anyways, when I'm talking about the intersections, I'm talking about where corridors meet at a given point. That's what I'm referring to as an intersection. And a dead end is simply where you're at the end of a corridor and you're hitting a dead end. So with that being said, what are edges? Edges is quite natural. In this idea of viewing it, you can think of edges as passages. Edges as passages connecting intersections and dead ends. So you might ask, Dan, why would we talk about a labyrinth? Like, why would we do this? I usually like to use this opportunity to talk a little bit about some of these things. I don't like talking about myself very often, but I find hearing about interesting stories is an interesting way of telling people how we might approach doing things. Now, for those that may have a fancy for mythology, I'm going to draw on the analogy of talking about the story of Theseus and the Minotaur. Or Minotaur, however you'd like to pronounce it. So I'm going to tell you a fun story. Now, it's an interesting story for many reasons. Now, how many of you have ever heard of Theseus and the Minotaur? If not, I'm going to give you kind of a basic summary of the story. There's several different ways and different interpretations of the story, but I'm going to give you kind of just a basic walkthrough of some key ideas, because we don't need all of the nitty-gritty bits of the story. So, anyways, for those that are not acquainted with this story, I encourage you to go check it out. It's a very interesting and classic story out of Greek mythology. It's along the ones of like Heracles and talk about Perseus. These are very interesting stories to talk about. Now, in Theseus and the Minotaur, I'm going to give you a basic setup for the idea here. So at one point, there was this king of Crete named King Minos, or King Minos, however you'd like to pronounce it. And he was in this predicament I'm not going to go into the details of. And in the process of this, he was offered a white bull. And this white bull was very, very beautiful. Now, this white bull, King Minos just looked at this bull like, he was given the option to sacrifice the bull in the story. And King Minos is like, nah, man, I'm going to keep this. And now this bull was supposed to be sacrificed to Poseidon, the god of the seas. And in Greek mythology, when it comes to sacrifices and things like that, they take it rather seriously. And Poseidon was like, hey, man, that bowl was for me. And what happened was Poseidon said, hey, look, you have your wife over there. Now, remember, this is just what happens in the story, okay? There's several different ways this happens, but I'm just trying to keep myself in composure. It's for me, not for you, don't worry. So King Minos' wife, Pasiphae, is basically put into a mode of deep passion for the white bull by Poseidon. So you might ask, okay, so what happened? Well, I like to keep things as innocent as I can in my stories, but for, I don't know, dirty-minded people like me, there was some part of the story where it involves Daedalus, this great inventor, creating and carving out a wood-crafted cow for her to climb into. And effectively what happened is the bull and the wife did this thing, and then we got the Minotaur at the end of this process, a half man, half bull. And I'm not even kidding, this is a part of the story. And now in this whole event, King Minos, to effectively put away his shame of this whole situation, he builds, with the help of Daedalus, the great inventor in Greek mythology, this incredibly intricate and ever-complex maze called the Labyrinth. And in the Labyrinth, this is where the Minotaur is hanging on out. Now you might ask, Diane, why is there this big complicated maze underneath the palace in Crete for King Minos to have this great labyrinth? Well, like I said, there's some conflict that was going on between Athens and Crete. Again, I'm not going to go too much into the details here for the purposes of time, but essentially there were being offerings made of girls and guys coming over from Athens to Crete, and effectively they were being walked down into this labyrinth for the Minotaur to slay and potentially eat. And now Theseus in the story was not a very big fan of where all of these people were just mysteriously going, and he ends up going to Crete to try to take down and slay the Minotaur. Now in his journey he runs into King Minos' daughter, Ariadne, and in the story Ariadne gives Theseus a ball or spool of thread, and what Theseus is instructed to do is to use this thread to help navigate through the labyrinth. Because if you think about it, imagine that you start off, say this is the entrance of the labyrinth. Imagine I tie this up at the beginning of the labyrinth somewhere. I can drop and leave down my thread. I can loosen it out. I can unroll it. And as I explore through the labyrinth, I can retrace my steps back through the labyrinth by winding back up the thread. But as I do this, I could do other things. For example, I could mark with chalk on the floor along the walls at an intersection, for example, and I can figure out where I've been versus places I've never been. So in the story, Theseus explores through the labyrinth by going through with this ball of string, effectively finding his way through the labyrinth, and slays the Minotaur, who may be somewhere in this maze. So now the natural question is, okay, so what happened? Well, I'll let you think about the story. I'm not even kidding about some of these details. They're rather fun in the story. Not fun for real-world circumstances, but they're interesting in the context of the story. But this is where the idea of depth first search is very natural to come from. If you think about it, what I'm going to do is I'm going to use this thread idea as almost the way of me examining what I've currently looked at and what I'm going to examine. And the way I'm going to put this ball of string or spool is effectively recursion. So here's the idea. Here's the idea. What we're going to do, we're going to unroll the string. So we're going to imagine we're Theseus going to go explore the labyrinth. So we're going to unroll the string as he explores. And we're going to mark each vertex. Sorry, I'm kind of in the way here. Mark each vertex and label each edge that we examine. So you can think of this like I'm running around with a piece of chalk in my pocket and I mark a big X on them. Or I might write or color them a little differently. So I'm going to mark each vertex and label each edge. And if I find no other places I could explore any further, I'm going to retrace my steps just like I'm winding back up the string. So I'm going to just simply retrace steps. Retrace steps if no more unvisited options for Theseus. So just to reiterate, we're going to unroll the string as he explores, mark each vertex, label each edge, and I'm going to retrace steps if no more unvisited options, that's an S there. It looks kind of like it's sad in the corner there. It says unvisited options for Theseus. My apologies for the writing here. It's a little, I'm going to get a different marker. Is somebody keeping a track of how many markers I go through, by the way? It's kind of funny. I'm hoping that this is a better one. Okay. So let's talk about how this will get done. So the very natural way of looking at what we're doing here is actually thinking about it recursively. So the ball, too many laws count. So you got to look at this thread like it's the recursion. And you might recall in recursion that we have a call stack, or you may know it as like the system stack. So when I do this process, I'm going to first try to walk you through how I might explore this. Then we're going to look at the pseudocode, okay? So I'm just going to erase this right here just to make this a little easier for us to go through an example here. So I want you to imagine that every time I examine a brand new vertex, what's going to happen is you're going to imagine it like I'm going to take one step into the maze, and each one of these is a call, recursively speaking. And as I go through the labyrinth, you got to imagine it like I mark and label respectively, so that when I make the next step forward, I know where I've been and where I have not been. So here we go. So imagine I start off at A here. So you're going to imagine this like a call stack, which this is how, when we actually see the algorithm, this is how it's going to be. Is you're going to see I'm going to do a recursive call starting at U. In this case, that's A. And here's what I'm going to recommend we do. Is every time we start at a vertex, we're going to mark it. And then we're going to go through all of the incident edges that it has. So remember, that means I'm going to examine this edge, I'm going to examine this edge. And each of these has obviously another endpoint. I may not have visited it yet. So every time I go through here, now, for the purposes of our algorithm, it doesn't matter which order you actually examine the edges. This traversal doesn't matter in this traversal. What matters is if we visited it or labeled it respectively. So for example here, I could examine this edge first. And the reason why I know I have not yet examined this edge is that if I look at the vertex here, I haven't marked it, right? I haven't marked vertex H yet. So what does that mean? That means I better explore from vertex H. So I'm going to start up by doing an exploration now from vertex H. And then I'm going to, remember what I said at first? I'm going to mark where I've arrived at. And then I look at all of my incident edges. And now you might ask, Dan, you don't have any edges that aren't labeled, right? Because remember, when I go and look at, I look at my incident edges, notice that this one is already marked, right? So that means I shouldn't go back in that direction and go treat that like I've never been there before, right? Clearly I've been there. I went there with a big piece of chalk and went like this to the wall over there. So that means I've already been over there. So that means I have run out of options here, but what do I do in my adventure? I wind back up the string and I retrace my steps when I run out of options. So that means I'm done exploring at vertex H, and now I'm going to continue back with what I was doing here, while I was going through each incident edge for vertex A, right? I already examined this edge. I look at this edge, I look at its other endpoint. Is this marked or not? Can somebody tell me, is vertex B marked or not? It's not marked, right? It's not marked. I've never been there yet. So what am I going to do? I'm going to label this edge, and then I'm going to now visit vertex B. Well, vertex B, the first thing I do is I just mark with a piece of chalk. I go like this on the wall. And then I look at my incident edges, right? Same idea as before. Now I can examine in any order I would like. Suppose I were to examine this edge here. Notice that its opposing endpoint is not marked, so I can go and proceed to go that way. So I'm going to label this edge as I walk over to C, and now I'm going to explore from C. So what's the first thing I do? I look at my incident edges. I look at all the edges that I have. Notice that this one's already marked. This other endpoint of this edge is already marked, so I know I shouldn't go that way. I've already been there. But here, notice that I have an endpoint here of this incident edge that is not marked. That means I have not been there yet. But in particular, one thing I really want you to notice is that whenever I do this, I only do it on unlabeled edges, right? Because there's no way I could have even been here if this isn't marked, because this edge here would have been the way I walked there, right? But I must stress that a vertex can be marked, but the edge may not be labeled. So I'm just planting a seed for something we're going to talk about here in a moment. But notice that I could walk over to D now, because I haven't been there yet. And I do the same thing. I marked D, then I look at my incident edges. Well, this one's already been visited, so I don't need to go there, right? This one is not marked though. So I'm going to label this edge. I'm going to go visit E. And now I'm going to mark E because I've already been there. But here's the interesting thing. Actually, before I do that, let's do it. Let's do it. Suppose that I look down this corridor. Suppose I'm Theseus and I look down this corridor. I see a big X on the wall. Do I need to walk over there if I'm trying to find new stuff? The answer is no, right? There's nothing over there. I've already looked. So what I'm going to do is, instead of labeling it with black like this, I'm going to label this edge a little differently, because that edge leads me to a marked vertex. But notice that I've already been to that vertex. So I'm going to label its edge a different color to make this a little easier for me, so I know I shouldn't examine that edge again. Because if it's labeled, then most certainly I've already considered it. So let's continue. So I'm not going to go down this way because I've already been there. So let's examine, let's keep going. So I find that I don't want to go this way, right? Because I've already been there. So let's consider, say, going this way. Let's suppose we go and explore down towards vertex F. So I'm going to label this edge, and then I'm going to explore F. Sort of running out of space here. I might have to erase a little bit more here. So when I get to F, I mark it. And then I look at my incident edges. You'll see quite quickly I have another edge here. And then I could explore. I'm sort of running out of space. I need one more to fit on here. Then I go and visit G. I mark it. I look at my edges that are incident to me. Now, so if imagine I examine this edge, because it's not labeled, right? So what color should I make this edge? What color should it be? Should it be black or red? It's red, right? Because remember, I've already been there. So most certainly Theseus should not go down that way. So now notice that I'm at vertex G right now, but all of my edges are labeled. So question, could we have gone to E instead of C? So yes, that is completely fine. That would be something you could totally do. The ordering of the edges I go and explore, it doesn't matter. Yeah, the order does not matter. Now, one thing I'll give you as a caveat to that is that it depends on how you implement the graph. So for example, if your graph if the way you represent the graph on your computer depends on the vertices themselves and the ordering they're given, it might pick the one with the lower index as opposed to one that's larger. But for the purposes of this algorithm, it doesn't matter. It does not matter at all. So notice that I could have went to E instead of C first, and they would not matter. We might get a different outcome for how I label the edges, but the point here is that I'm still going to explore the graph regardless, all of the ones that are reachable from U. So now, this is where things get interesting. So now, remember in the story I told you, just like when I got to vertex H, I roll back up the thread when I'm walking myself back, right? So I'm all the way over here. So I'm all the way in G, but I have my one end of this thread still tied at about A. So what am I going to do? I'm going to start retracing my steps, because notice that there are no more options for edges for me to explore anymore at G. So I'm done exploring at G. Now I go back to F, because remember, this is where I rolled my thread out, because this is where I was. But notice, I want you to notice very carefully, is that the thread that I actually have is everything that I have on the call stack. Notice at the top of the call stack is where I need to go next, because I'm retracing my steps, and retracing my steps corresponds to the call stack. So you're going to see that the algorithm I'm going to give you is recursive, but you can always transfer and transform it into an iterative version if you liked. But we're not going to focus much on that here. So if I'm at F, I'm done examining all the edges, so I'm done there. Now I'm at E. I'm done examining all the edges, right? So I'm going to retrace my steps back to D. Same idea here. Now I'm back at C. No more edges to examine. In particular, no more unlabeled edges, right? So, and then I go back to B. And notice that now I'm back at A. But I've considered all of my edges. And then I'm done. But notice at the end of this process, every vertex is now marked, and every edge has been labeled. So isn't that kind of cool? So the two things I need to point out for you is that we actually have special names for these types of edges that I've colored here. The black ones. So the black edges. These are called discovery or forward edges. I'll sometimes call them discovery edges, but they're sometimes also called forward edges. The red edges, these are what we refer to as back edges. So the red edges, these are back. These are back edges. So any one of those red ones I would call a back edge. All the ones that are black, I call them discovery. Each one edge is called a discovery edge. So that leads me to talk about the algorithm itself. So first, does everybody sort of get a feeling for what the algorithm might look like? So notice that every time I mark the vertex, then I start considering all of my incident edges. So you'll have a loop that's going to examine each one of my edges, incident to mine. And then I'm going to go through each one. If it's unlabeled, then I'm going to consider it. I look at its opposing endpoint. I say, hey, look, is the other endpoint marked or not? Well, that's going to tell me right away if I need to keep exploring. And if I have a place that I could go with that, I go to recursively call on my exploration again at that vertex. So let's do the pseudocode out, and let's see how this actually looks when I write it all out like this. Whoops, the camera's decided to go on a little trip there. There we go. But isn't this neat? So now this is one way we could explore the graph. So let's write out this pseudocode for depth first search. So let's talk about depth first search. So let me give you the algorithm. So we have DFS. So I'm going to call it DFS. I'm going to be given a vertex U. So the input, so here's the input. The input is going to be a vertex U among the vertices of the graph. And now one thing I'm going to presume when I write out the pseudocode here is I'm going to presume the graph is connected. But I must stress that this algorithm doesn't actually require that. It just will only reach vertices that are reachable from U. So you can totally apply this algorithm to a graph that's disconnected, but it most certainly won't explore every vertex, right? It won't be able to reach all of them by definition because there's no path from each vertex to every other one, right? There's going to be some that are going to get left out in this process. So of a connected graph G is equal to VE. And as output, now I'm not going to return anything here. And I must stress that this algorithm is more of a broader framework. So you can easily modify DFS to do all sorts of fun things as we're going to see today. So I'm going to be showing you some fun applications of DFS once I give you this general breakdown of how we could explore the graph. So here's the output. So I'm just going to assume it's going to give us a DFS traversal. That's what I would refer to as a traversal of the graph using DFS, or depth first search, is a DFS traversal. That's what it's called. Of G starting at U. So it's not going to return anything. It's just going to modify the graph. If you ever wanted to make it return anything specific, you're welcome to modify this algorithm a little bit if you like. I'm just going to modify the graph. So what was the first thing I said? I start by marking. So I'm going to imagine I have some function. I can give it a vertex and it will mark it. So I'm going to refer to that as mark, and I'm going to give it a vertex. So that's what mark does. It just marks vertex U. So that's the first thing we did every single time, right? And then I go through each, so for every edge, UV, so I'm going to look through all the incident edges of vertex U. So I'm going to go through each one of those. I'm not going through every edge of the graph. I'm only going through the incident edges on U. So for every edge where U is one of the endpoints, we're going to do the following. So if the edge UV is not labeled, because if it is labeled, we don't really care about it, right? For us. So if the edge UV is not labeled, then we check if the other endpoint is marked, right? If V is marked, then we're going to label it. Now I have a question. Remember back to our example we did over there. When I was labeling the edges, I had labeled them black for forward or discovery edge, and I had red for the back edge. So, a question. If you know that the edge is not labeled yet, and the other endpoint is marked, what kind of edge should this be? Should it be a discovery edge or a back edge? It's a back edge, exactly. So here I'm going to label as back edge. So I'm going to label UV as a back edge. So I'm just going to, for some reason my B looks like an H. Let's fix that. Label UV as back edge. Otherwise, we're going to label that edge as a discovery edge. label UV as discovery edge. So I label it as a discovery edge otherwise, because now I have someplace I could go explore. And all I'm going to do is recursively apply DFS now on V. And we have the end of the if statement, end of the for loop, and that's it. That's DFS. Boom. So that's DFS. So you might ask, Dan, first, are there any questions about this pseudocode before we proceed? Any questions at all? Or are we all good to go with this? I'll give you another moment to copy this down. So while I'm waiting here, one thing I want to point out here is you'll notice that I made no assumptions about how I represent the graph. So you're going to find that when I give you a graph algorithm, oftentimes, just like when we talk about other data structures, the underlying representation of that data structure may play a very much a key role in how its time complexity can play out. In this case, there's sort of pros and cons, but generally they level out. But I will talk briefly about each one. I have the full analyses in the notes. But I want to walk you through kind of what we usually do when we analyze an algorithm, right? So I'm going to identify all the operations that occur and how many primitive operations or elementary operations occur. We're going to count those up, then we're going to see what happens, depending on what the representation of the graph is like. So let's look at this. So first thing I should tell you up front is I presume that I can mark in constant time. So let me just get a different marker here because it makes things a little easier. My apologies for the crinkling noise there. Crinkling is not fun when it's close to a microphone. So we know right away that there's kind of this part where I mark. I have, now remember, this is a recursive algorithm. Now, typically when you analyze a recursive algorithm, first we start off by ignoring the recursion. Then we count up all the operations that happen. And then we introduce back in the recursion and figure out how many calls could possibly happen. Or figure out some relationship those calls have with the algorithm itself and how it modifies it. So first, we're going to ignore the recursion. So I'm just going to treat this like it takes a constant number of operations to call DFS on V. So you'll notice very quickly that since I can check a label of an edge in constant time, that all of this inside of here is some constant number of operations if I ignore the recursion, right? So all of this takes some, we'll call it C2, we'll call the marking C1. And you might ask, okay, so Dan, the number of operations that happen with this for loop depends heavily on the number of incident edges, right? But remember, the way I represent the graph can actually change how long it takes me to compute those. So the overall number of iterations or number of operations I need here is C2 times the number of iterations of the for loop. That says number of iterations. So I would like to figure out what the time complexity is overall. So you can see quite quickly that if I give you a vertex U, the total amount of operations is going to be at most C2 times the number of iterations of this for loop plus C1. Does everybody see that? Does everybody see that? So what I need to do now is I need to justify how this ties all together with the recursion. So let's talk about that, okay? So why don't we head over here and let's talk about how we stitch together what we have here with the recursion. So let's head over here. Is everybody having fun? I'm having a blast here. It's always fun getting to play around with graphs. So let's talk about the time complexity here. So let's talk about the time complexity. So you'll notice that this algorithm is rather oblivious to what happens in terms of what the structure of the graph looks like. It's really oblivious to all of it. So I'm just going to focus on just thinking about the worst case time complexity as just the time complexity. So you're going to notice very quickly that I'm going to invoke a lot of things that we talked about with graphs to make the analysis go a lot smoother. So I'm going to proceed past the part where I derive those constants, and I'm going to observe that the algorithm visits every vertex in G exactly once. So question, why is that true? Why is it that every vertex in G is visited exactly once? So think about it from the perspective of the algorithm. Why do I only visit a vertex once? And only once? So do you remember how when I did the exploration, what happened? Yeah, it's because, it's marked, right? You don't go back to a vertex that's already marked, right? You don't go and explore over and call DFS, right? You just simply say, hey, look, that one's already marked. I'm not going near there, okay? I'll be back there later when I come back winding through the graph. Just like I'm going through with my thread. So that's why. It's a very good, very important observation here. Thus, the total number of calls, so this is me counting including where we started, right? Total number of calls, so I'm talking about the calls to DFS U, where U is whatever vertex I call it on. The number of calls is the number of vertices. Semicolon. This implies the time complexity. The time complexity is the following. Since I do the C1 plus the C2 times the number of iterations for each vertex, it is the following. I just sum over all of the vertices. So I go over all the vertices, I sum over each one, and I have C1 plus C2 times the number of iterations, right? So if I can figure out kind of these blanks here, like, I don't know that. That seems to play a very important role in how the time complexity is going to play out for us. So the number of iterations is very closely related to the representation of the graph. But all I have to do is figure out this, and then I can figure out the time complexity for if I give you an adjacency matrix or an adjacency list. Does everybody understand the idea? What we're going to do next is we're going to look at what happens when the graph is represented as an adjacency matrix, and then we're going to look at it when it's an adjacency list. But all I have to do is tell you what happens with this. Does everybody see that? This is one elegant thing about the analysis that you can pull out from DFS. So I like to show it this way so that you can see how the representation actually plays a very important role in the time complexity. So let's talk about first the adjacency matrix. So the adjacency matrix. So you might think, okay, well, I want you to recall, when I go through that loop, what does it do? It goes through each edge that's incident on my vertex, right? Vertex U. It goes through each one of its incident edges. But do you recall how long it takes me to compute the incident edges on an adjacency matrix? if I give you a graph with n vertices, how long does it take to compute the incident edges? I know, because I asked you guys this last time. Does anybody remember? So any ideas? Anybody remember? What was it? What was the time complexity computing the incident edges? So I want to figure out all those incident edges, right? So let's think about this. So remember, it's for a given vertex, just one vertex I'm looking at right now. So vertex U, I want to figure out all the edges that are incident on it. Now we don't need quadratic time. We don't necessarily need that. But that's over all of them. We aren't quite there yet. We're just looking at one vertex when I want to figure out the edges. So to consider each edge UV incident on U, we must, in the worst case, traverse n entries of a row of the matrix, right? Remember I said that the other day. So the question is, how long does it take me to compute the incident edges of a given vertex? So it's not constant. It's not constant. It's linear. Yeah, it's big O of n. Implying the number of iterations of the for loop is at most n, right? So you might say, okay, let me just, there we go. There we go. I had to take that little extra tail off the end, okay? It wanted to go for a walk. So when I put everything in, so I'm just going to proceed back to what we have here. I'm just going to plug it in. So now I know that the number of iterations is at most n. So it is the sum over all the vertices. Sum over all the vertices. I'm going to have C1 plus C2 times n, which if you expand this out, it's C1 times n plus C2 times n squared, which this is big O of n squared. So for an adjacency matrix, doing DFS, it takes quadratic time, but it's quadratic in the context of the number of vertices. Now, one thing I must stress is that when you see a quadratic like that, I must stress that what you're actually looking at is actually a relationship it has with the number of edges. Because remember, the number of edges a simple graph has is at most something that looks like n squared, right? So just keep that in the back of your mind when you think about that quadratic there. Because it is quadratic in the number of vertices. But in terms of the number of edges, it's technically at most linear in the number of edges. But that's just sort of an aside. So if your graph is really dense, this is not bad at all. It's actually quite nice, right? So let's talk about the adjacency list then. Because the adjacency list is the interesting one. This one is just, okay, so whatever, man. It's Monday, Dan. What are you doing here? So let's talk about the adjacency list. So this one I'm going to go a little faster. I have a more complete analysis in the notes. But I think that we have a good idea of what we're trying to accomplish here. So if I have an adjacency list, so suppose I have an adjacency list. Question. So if we want to compute, if we're trying to compute, or we're computing the incident edges of a vertex U, how long does that take me with an adjacency list? So remember, imagine you have one of those linked lists. I index in, and I go look at the linked list. In the worst case, I'm going to have to traverse the entire linked list. And the question is, how many nodes can there be in this linked list for our adjacency list? So how many nodes can there be at most? Now, I'm not looking for n, because technically speaking, you could say, okay, well, every edge, so I can have entirely filled up, but that's not really, that is an upper bound on how many. There's actually an exact number of how many there are. There's an exact number. So I'll give you a tip. Do you remember that I'm really trying to know how many incident edges there are? But what does that mean? What is that definition-wise? What is that? Starts with a D. Starts with a D, ends with an E. Yeah, the degree. Exactly. It's the degree. So if I want to compute that, well, what is that? So requires, in the worst case scanning at most the degree of U elements. So all I do is now I'm just going to use the same guy I had over here, and I'm just going to plop it right in for number of iterations. So all I do is the following. So it is, that says it's sort of hanging really close with the I there. So it is the sum over all the vertices. So I have C1 plus C2 times the degree of U. Well, this first one here is just, okay, there's n vertices, right? So it's going to be C1 times n when I pull, because remember, this is just some constant times how many times it's added up, right? So this, however, is a little bit more interesting. So I'm going to write that out more explicitly. So it's going to be the C2 times the sum over all of the degrees over all vertices. Over all the vertices. But what is that? What do I have right there? I told you there's this really cute result, and and every once in a while it just sort of pops up. What can I replace with that sum I have over there? Well, I'll remind you, by the handshaking lemma, the sum over all the vertices, is equal to 2 times the number of edges. And the worst case time complexity is C1 times n plus C2 times 2 times m, which this is big O of n plus m. Keep in mind, both of those you can replace with big theta. Usually when I say big O, I usually mean big theta. So let me just, I'm just going to switch my earphone piece. It sort of just died on me. So let me just switch that. My apologies. But yeah, so when you look at this, now we can say that DFS takes time linear in the number of vertices and the number of edges. So this is a linear time algorithm, which is sort of sounds kind of weird for me to say that, but really remember, the graph size is actually dependent on the number of vertices and the number of edges. So this over here is rather effective for the adjacency list, because if you recall, the space requirements of an adjacency list is the exact same, right? Just like with the adjacency matrix, the space requirements there match also what I have over there for the adjacency matrix. Isn't that wonderful? So, are there any questions before we proceed? Is this kind of neat? So we have these really nice traversal algorithms that traverse in linear time, at least with respect to our number of vertices and edges, over the graph. So one natural question is, Dan, I assume DFS starts at some vertex and you presume that the graph is connected. I wanted to ask sort of as a discussion point, I have the answer in the notes. I would like you to take a quick peek at that after class. It's a question, it's a very natural question. Suppose that the graph isn't connected. How can I traverse the entire graph? Any ideas of how I can achieve this? Now, it doesn't have to be the most efficient way of doing it. My apologies, I'm getting very excited here. Teleportation. It almost actually works like that, actually, but it isn't literally teleportation. That's a very good place to start, though. So you can imagine it just like that. So imagine you explore one connected component of the graph. Is there any ideas of what I can do to explore other parts of the graph? And I think the idea of teleportation in the abstract sense, not in the literal sense, is actually a very natural way of thinking about this. So for those that aren't a big fan of teleportation, you can always think about the algorithm as I'm bootstrapping the algorithm and I'm starting it up all over again, but I pick another vertex that is not marked. So yeah, call exploration again. Yeah, exactly. Exactly. So all you have to do if you want to explore the entire graph is you can imagine you just have a for loop. See if you have this master version of DFS, and you just simply have it where you have a loop that goes through each vertex, and you ask the question, is the vertex I'm examining marked yet or not? If it isn't marked, then you better run DFS on it. So you just scan through all the vertices, you just check each one of these and just ask, is it marked? If it's marked, you better not run DFS on it because it's already been explored, right? So it's very nice, right? So all you have to do is you just restart up DFS on an unmarked vertex. And you might ask, Dan, does that affect the time complexity? And here's the fun answer. The answer is no, it doesn't. It still maintains these same time complexities. So I'll leave you to think about that. It's actually just in the notes here. Now, the easy justification for you, by the way, is you notice that if you go through each of the vertices, if you think of it just as a for loop that goes through each vertex, notice that each time I call DFS, but when I actually do it, when I actually call DFS, it's on an unmarked vertex. So I never call DFS on a marked vertex. So it means when every time I do this, you can almost like if I count up all the operations that happen for all the DFS calls, all of them are going to be linear in the number of vertices and edges that are a part of that connected component. But those never cross over with each other, right? They're different parts of the graph. So when I count up all of those operations and I take each one from each connected component, it's going to actually sum up to what I have over here. Just with this extra for loop, it's just an extra linear term of n, and that gets consumed by the asymptotic notation. But isn't that neat? So it's very easy to adapt if you want to just explore the graph. So one natural application as a result of this is to talk about whether you want to test if the graph is connected or not. So based on what I just discussed with you, how can I test if a graph is connected or not? Any ideas? So how do we do that? Any ideas? Yeah, you have a so we see, have a counter to see how many times you need to call DFS. It only calls once, it's connected. That's a good suggestion. I'll give you an even cuter way of doing it. That's one valid way of doing it. Notice that if you only call DFS once, that means that you had to have marked every vertex, right? So all you have to do, if you really think about it, is just... So you just pick a vertex to start at. So run DFS. So you just pick any one. So just pick any one vertex. If any vertex is unmarked, sorry, this unmarked looks melted like it's in the microwave. And if any vertex is unmarked, what does that imply? It implies it's disconnected. So all you have to do is you just modify the process I just described to you, where you just start up DFS but remember, you don't have to restart up DFS, you just simply scan through all the vertices instead of just starting it up again. You just pick any vertex, you run DFS, then you scan through the vertices. If any one is left unmarked, then you know that it's definitely not connected. But yeah, wonderful, wonderful. So that's one thing you can do with DFS, is determining if a graph is connected or not. It's rather natural. Now I want to talk a bit more about some more applications we can do with DFS. So let's talk about that. So that's one you can do. You can test if a graph is connected or not in linear time. That's one natural thing you can do. So one that I'm going to talk about, which is because I'm looking at the time here, I thought I would kind of knock out some of the lighter applications first. Then I'll leave probably the more substantial one for next time. I was hoping to cover it first, but let's start with some of the lighter ones, just to get ourselves warmed up, okay? So here's the first application I want to talk about that we can do. So we can do so-called cycle detection. This one's it's rather cute, but it's rather effective. So, question. Do you recall at all, suppose that I gave you a graph that looks like this. Keep in mind, we ought to think about any graph. We're usually presuming that these are undirected graphs, but these are very easy to adapt to be directed graphs. So suppose that I have a graph that looks like this. You can see quite clearly that there's a cycle in this graph, right? You just take a walk from A back around to D, then you come back to A, right? So when I do DFS, and suppose I start DFS at A, you recall that if I were to say, for example, begin by going towards B, remember I mark this, I go this way, I mark this, I'd go this way, I'd mark this, I'd go all the way to D, right? What do I label this edge as? What color should that be? What kind of edge is that? It's red, right? This is the back edge. So believe it or not, I've actually given you a key ingredient for detecting cycles, believe it or not. So back edge. So back edges can be used to form a cycle. So do you see how? So notice that if I had my process, and this is true for any graph, by the way, is if you were to start at some vertex, you go through, you follow the path that gets you to a given vertex that has a back edge incident on it. And it gets you back to the beginning or any part in between. There's a way you can formulate and build a cycle by using the back edge. So you can take and clip off the snippers. Like say if you have a path that kind of starts off all the way over here, and maybe there's some more over here that happens. You could take like snippers, cut off these parts of my tracing process where I label the discovery edges, and I could form whatever's left into a cycle using the back edge. So this actually gives us a very easy condition to check for a cycle. So here's the idea. So here's the idea of how we're going to proceed with this. Observe that if DFS labels an edge as a back edge, there must be at least one cycle. So what happens is we can actually use DFS. We can even specialize it, which I'll give you pseudocode for this in the notes. So we can specialize DFS to detect cycles. And like I say, one thing I want to point out is that everything I'm showing you with these applications, they share the same time complexities as DFS does. So the modified version I'm going to give you in the notes, so I'll just say C pseudocode. So if you actually want to do the time complexity analysis, it will actually be very similar, if not the same, as the one we actually walked through just a moment ago. So that's why I'm saying DFS is like a general framework, not just a general traversal algorithm. It also can be almost look like as like a skeleton that I can specialize to solve specific problems on graphs. So in this case, all I need is the part of DFS that detects the back edges. If I can detect the back edge, then boom, I can tell you if there's a cycle in the graph or not. That's one neat thing you can do with DFS. Another one that I want to talk about, because I have enough time to cover this next one, is we're going to talk about counting vertices. So suppose I want to count all the vertices in the graph, or for example, in a given connected component, if we want to be a bit more specific. So the first thing I want to point out is that notice that we visit each vertex once. It is when we mark the vertex, right? So we're going to use this. We're going to use this fact to count reachable vertices. So if I want to know all the vertices that are reachable from a given vertex, I can use this fact of DFS. So let me write out some pseudocode for that. So let me just see where I'm at. Just want to make sure I get this. Counting. Where's my counting? Ah, here we are. My apologies. So you're going to notice that this is going to look like a very stripped back version of DFS. It's going to look much simpler. So here we go. Let's look at the algorithm. So So here's the algorithm. I'm going to call it count vert. Count vert. And imagine I give you some vertex. So count vert's job is just going to be to count all the vertices. For some reason, my brain is melting. I'm just so excited here. So let's see here. So input, I give you a vertex, u in the set of vertices of graph g is equal to VE. And the output is the number of vertices. Number of vertices reachable. So I thought this would be a nice way to finish off the lectures because we talked about reachability at the beginning of the lecture. I thought I would end off by showing you how to actually count them. So thought it would be nice and suitable for this. So first, like we did with DFS, we're going to mark the vertex. Then I'm going to have a counter. Because remember, every time I mark a vertex, that means I visited a unique vertex. So I'm going to have a counter. I'm going to start it at 1. Then I go through for each edge. So I go for each edge incident on U. We're going to do the following. We just simply ask if the other endpoint is marked or not, right? If V is not marked, then we increment our counter. So we say count is assigned count vert. So we're going to recursively call count vert on that vertex if it's not marked, right? Plus count. And then we're going, that's it for the for loop. And then all I do is I just return the number, return my count. It's a little squeaky. So believe it or not, look how stripped back this is compared to the DFS I showed you. Isn't this nice? So I could use, so notice that we're using properties that DFS has in each one of these cases. Like when I count the cycles, I look for a back edge. In this case, I use the fact that I mark every vertex exactly once. So notice that here, all I do is I mark. I have a counter because when I marked myself, that means that I'm counting myself. And then I go through each one of my incident edges, and I can continue the search over vertices that are not marked. So you can see that this algorithm actually will have the same time complexity as DFS. You'll notice all it is just a stripped back version of DFS. It's just specialized. Just like when you see the cycle detection algorithm, it's very similar there too. So with that being said, I'm going to include it in the notes, but the next application we're going to see is how we can compute a path from between two vertices. So if I give you one vertex and another vertex, I would like to know how to compute a path between those two vertices. So a path from, say if it's A and B, I want to know the path. So I'm going to show, I'll put that in the notes too, but we'll start with that next time, and then we'll talk about our next graph traversal algorithm. Okay, everybody? So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.